Welcome to this explainer. Today, we're going to peel back the onion on complex mathematical equations to reveal the stunning physical, geometric reality underneath. It is so easy to get bogged down in formulas and totally lose sight of what the math is actually doing. Well, today, we're going to change that. So let's dive right in by asking a question that seems, honestly, almost impossible to answer. What could a massive physical structure like a suspension bridge possibly have in common with an AI algorithm crunching data in the cloud? I mean, they seem worlds apart, right? But underneath the steel and the silicon, they actually share the exact same mathematical DNA. To understand how that's possible, here is our agenda. 1. Structuring the messy world. 2. Finding the real information. 3. Arrows that never turn. 4. The secret scaling factor. And 5. When bridges start shaking. Section 1. Structuring the messy world, from chaos to matrices. We obviously don't just magically start with clean grids of numbers. We start with a messy reality that desperately needs organizing. Think about a standard system of linear equations. You've got multiple variables, intersecting lines, just a chaotic jumble of numbers trying to find a single intersection point. Well, instead of dealing with those chaotic equations individually, we represent them in a much cleaner form. A times x equals b. By extracting the numbers into a coefficient matrix, we basically turn a messy real-world problem into a clean, structured computation. It's absolutely the ultimate organizational tool for complexity. Section 2. Finding the real information. Discovering matrix rank. Once we have everything organized into a matrix, we have to figure out if all the data we've collected is actually useful, or if it's just redundant noise. This brings us to a crucial step: figuring out the foundation, or the basis, of our system. A basis is essentially the minimum set of fundamental directions you need to build your entire space, and we measure this using the rank of a matrix. Rank tells us the maximum number of linearly independent rows or columns. Basically, if one row is just a multiple of another, it's redundant. The rank cuts through the noise and reveals the true independent dimensions of our system's reality. And this transforms directly into physical geometry. A rank of 0 means we have a zero matrix. Geometrically, that's literally just a single point at the origin with 0 dimension. A rank of 1 means all our data falls strictly along a single basis line. It only spans 1 dimension. But a rank of 2? That means our independent rows span a whole 2D plane passing through the origin. So the rank literally draws the dimensional space that our system lives in. Section 3. Arrows that never turn. Invariant directions. We have our geometry, right? But systems aren't static. They transform. So what actually happens to this geometry when we apply a linear transformation, like, say, stretching or rotating the space? Well, most vectors get totally thrown off their path. But an eigenvector is incredibly special. Think of spinning a globe. Every single point on the equator is moving, but the axis running right from the north to the south pole stays exactly where it is. That axis is an eigenvector. It refuses to be knocked off its original line, acting as this invariant foundational pillar for the entire transformation. To really visualize this, imagine an initial state as a perfect blue circle. When a linear transformation is applied, that entire blue circle stretches out into a green oval. Almost every single point inside that circle completely changes its direction relative to the center. But notice that specific purple arrow. It never turns. Sure, it gets a bit longer, but its fundamental direction remains absolutely locked in place. That is the sheer power of an eigenvector. Section 4. The secret scaling factor, decoding eigenvalues. Let's see how our invariant arrows build into our next major concept, the hidden engine driving the transformation. If the eigenvector is the arrow that never turns, the eigenvalue, which we represent with the Greek letter lambda, is the number that dictates its fate. It tells us the exact factor by which that specific arrow is stretched, squished, or reversed. In a real-world system, you can think of the eigenvalue as the energy or the strength along that specific invariant path. It is the secret scaling factor that determines just how aggressively the system is moving along that unchanging direction. And these numbers aren't just abstract math. They give us immediate physical intuition for how the system behaves. A positive eigenvalue means the system is stretching outward in that direction. A negative eigenvalue? That means it completely flips and stretches. If you had a complex eigenvalue, well, then the system is producing rotation or oscillation. And magnitude matters immensely here. The largest absolute value will absolutely dominate the system's behavior in the long run. Now, to find these magical values, we use something called the characteristic polynomial equation. And doing this reveals some deeply beautiful systemic connections. For instance, the matrix determinant, that's actually just the product of all the eigenvalues. The trace, which is the sum of the diagonal elements, that's equal to the sum of the eigenvalues. And if an eigenvalue happens to be 0, it directly impacts the rank of our matrix, mathematically proving that the system has collapsed a dimension. It is all brilliantly interconnected. Section 5. When bridges start shaking. Math in the real world. This brings us to the climax of our explainer. Why does this theoretical geometry matter in physical engineering? Well, imagine a massive suspension bridge vibrating in the wind. Most frequencies are completely harmless. They just get absorbed by the structure. But what if the wind hits the exact frequency of the bridge's dominant complex eigenvalue? The system's hidden natural mode gets activated, and those complex eigenvalues predict a catastrophic oscillation. The math literally tells us exactly how and when that bridge will tear itself apart. Because eigenvalues fundamentally predict whether a system is going to grow, decay, or become totally unstable, without needing exhausting full-scale simulations, they are the ultimate predictive tool. In artificial intelligence and machine learning, we use principal component analysis to find the eigenvectors with the highest eigenvalues. This means we can compress massive datasets just by keeping the data's most important structural directions. From stabilizing robotics to managing entire power grids and signal processing, this math decodes the future state of basically any linear system. Ultimately, this geometric intuition, understanding rank, finding those invariant eigenvectors, and analyzing the scaling eigenvalues is what elevates simple rote memorization into real practical engineering. Or, as one of our sources perfectly summarizes, you move from basic representation to system behavior understanding, which is basically the difference between someone who just writes equations and someone who truly understands systems. I really hope this explainer has profoundly changed how you look at the math structuring our world. It's clearly not just numbers. It is the hidden DNA of reality itself. But I'll leave you with this final thought to ponder. As you go through your day, what other hidden mathematical systems are silently governing, stabilizing, or even threatening the physical objects you interact with every single day? Keep looking deeper, and thanks so much for joining me.